Hi, on this chapter, I'm going to talk about solutions. Let's start this chapter by the definition of the solution. Basically, what do we mean by solution? Solutions are homogeneous mixture consist of two parts, solute and solvent. Solute is the substance that's present in lesser amount, and solute is the substance that's present in a larger amount. For example, if we dissolve sugar, okay, and these are sugar, in water, okay, then sugar becomes your solute and water becomes the solvent. Okay, this is a homogeneous solution. Once sugar is completely dissolved in water, it makes a homogeneous mixture. That means the texture is uniform. Everything is in one phase. And when the solvent is water, as it's been discussed in the past, that solution is an aqueous solution, which we will show it with a shorthand aqueous. That means whenever water is the solvent. Then when we dissolve sugar in water, we form an aqueous solution. Next, we're going to talk about different types of solutions. Okay, we studied three different types of solutions in this chapter. One is the solution of gases. It's like the air that we breathe in. It consists of oxygen gas, carbon dioxide gas, nitrogen gas, gaseous water. These are all solutions of gases, and it's a homogeneous mixture because everything forms a uniform phase. The second type of solution that we study is an aqueous solution. Then by definition, whenever water is the solvent, it's an aqueous solution. In this particular example, sodium chloride, which is an ionic compound, it's dissolved in water. Then it produces an aqueous solution. Then the state of NaCl is an aqueous state, and it's an ionic compound. That is why it will separate into sodium ion and chloride ion. Okay. And the third type of solutions, it's when a liquid is dissolved in a solid. Okay, this is not very common, unlike the other two. The example is when mercury 1 which is liquid, is dissolved in silver, which is solid. Okay, that's also a solution, which is a liquid and a solid. Then, as you could see in this particular example, liquid mercury is dissolved in solid silver. Then these are the three different types of solution that we talk about. Now let's go back and talk about conductivity one more time. I talked about conductivity toward the end of chapter 4 and chapter 5. Basically, we have two types when we talk about conductivity. It's electrolytes and non-electrolytes. Then electrolytes are those substances are capable of conducting electricity, and non-electrolytes, they are unable to conduct electricity. Then for electrolytes, then ionic compounds in aqueous state, strong acids also in aqueous state, and strong bases are all good conductors of heat and electricity, or they are electrolytes. Non-electrolytes are ionic compound ionic compound in solid state and molecular compound in any state. Okay, it could be solid, liquid, gases, aqueous. Okay, in any state, they are incapable of conducting electricity. Okay, then for electrolytes, ionic compound in aqueous state, strong acid, strong bases. Okay, they are good conductors of electricity. And non-electrolytes, ionic compound in solid state and molecular compounds in any state. Okay, then as you could see in this example, that's an example of sodium chloride in aqueous state, and as you could see, it will dissociate into the ions that it is made out of. That's why it's those positively and negatively charges that becomes good conductor of heat and electricity. Whereas on the second example, hydrogen peroxide, as you could see, is made of two nonmetal. Okay, therefore it's a molecular compound. No matter what the state of it is, it cannot conduct electricity because it's not made of ions. Okay, that's why it will not dissociate. It remain intact. That's why hydrogen peroxide in this example, okay, that's hydrogen peroxide. Okay, as you could see here, it cannot conduct heat or electricity. It's a non-electrolyte. Whereas sodium chloride in aqueous state, okay, is a good conductor of heat and electricity. It's a good electrolyte. Now let's talk about solubility. By definition, solubility is the amount of solute that you could dissolve in a given amount of solvent. Okay, usually it's reported in grams of solute per 100 milliliter of solution. It's the solution and not the solvent. Just make sure to take a note of that. Okay, then by definition, solubility is how much of a solute you could dissolve in a specific amount of solvent, and it's reported in grams of solute per 100 milliliter of solution and not solvent. It's the solution. Solution, it's solute plus solvent. Okay, that's what the solution is. Now let's talk about different types of solution. The first one is a saturated solution. When we talk about a solution being saturated, that means you could have added the maximum grams of solute that you could add, and you could still end up with a homogeneous solution. Okay, then when a solution is saturated, it has reached its maximum amount of solute. That means if you add tiny bit more, that solution is not homogeneous anymore. Okay, because some of the solid is going to precipitate out. Unsaturated solution, that means you could still add some more of solute and your solution still stays a homogeneous solution. That means your solvent has not reached its maximum number of grams. That's an unsaturated solution. Now, what is supersaturated solution? A supersaturated solution is when a saturated solution, you have a solution that has reached its maximum amount of solute. But then what you want to do, you want to add more of the solute. Then what you will do is you heat up the solution, and by heating it up, you could still add some more of the solute. Okay, but as soon as you remove the heat, those excess solute that you added is gonna precipitate out. Okay, that's a supersaturation. Then we achieve supersaturation through heating at increased temperature. But as soon as the supersaturated solution cools off, those extra amount of solute that you added gonna precipitate out and it's gonna form crystals. Now next one is concentrated solution. Okay, when a solution is concentrated, that means it has a large amount of solute. When a solution is diluted, that means it has a small amount of solute or large amount of solvent. Okay, for example, you make your coffee in the morning and it's very dark, it has that bitter taste. That means it's concentrated. Once you pour in more hot water, it becomes diluted, it becomes milder. That's why we call it diluted solution. Okay, then that really thick coffee in the morning, which has a lot more coffee grain than water does, it's a concentrated solution. And once you add some more hot water, it becomes diluted. Okay, that's the difference between concentrated and diluted solutions. Now let's talk about continue with solubility. The key is that when we talk about solubility or when we talk about what can be dissolved in what, the rule is like dissolve in like. What do I mean by like dissolve like? Then what happens is that ionic compounds, okay, ionic compounds and polar covalent compounds are soluble in water, okay, or any polar solvent. Okay, then just know that polar compound are soluble in polar solvent. Okay, then if you could see in this example, sodium chloride is an ionic compound. Okay, that's why you could dissolve it in a polar solvent. Okay, or water. Water is a polar solvent. Okay, this is the structure for water, which is a polar solvent. Okay, then I don't want you guys to realize the structure or what is a polar solvent, what is not. All I want you to know is that ionic and polar covalent compound are soluble in polar solvent, which water is a polar solvent. Okay, and non-polar compounds let me go back here, and non-polar compounds are soluble in non-polar solvents. Okay, that's all I want you to know from solubility for now. I will talk about it more in detail later on in later chapters, but what I need you to know is that like dissolve in like, and what I mean by it is that ionic and polar molecular compounds are soluble in polar solvents, as you could see here, and non-polar compounds are soluble in non-polar solvents. Okay, the example of non-polar compounds and solvents, a lot of the organic compounds, okay, they are non-polar. Okay, and let's go back here. Here is little extra side points. Here I talk about hydrogen bonding. Hydrogen bonding, it's the bond between hydrogen with either nitrogen, oxygen, and fluorine. Okay, that's a hydrogen bond. Then when hydrogen bonds with either nitrogen, oxygen, and fluorine, this bond right here is a hydrogen bond. Okay, hydrogen bonds are also soluble. Hydrogen are also soluble in water. Okay, then because if you look at the structure for water, it's like that. Water is also a hydrogen bond, because as you could see, it's a bond between hydrogen and oxygen. Then all hydrogen compounds, all compounds containing hydrogen bond are soluble in water, because water also contains hydrogen bond. Then let's review this one more time. When we talk about solubility, we talk about like, dissolve, like. And what I mean by that is that ionic and polar covalent compounds are soluble in polar solvent, which water is also a polar solvent. And those compounds that contain hydrogen bond, which is a bond between hydrogen with either nitrogen, oxygen, or fluorine, those compounds that consist of hydrogen bonds are also soluble in water. Why? Because water also contains hydrogen bonding. Okay? And last one, non-polar compounds are soluble in non-polar solvents. Okay? Like if you look in this example, octane, okay, which is an organic compound, and it is non-polar. It's easily can be dissolved in carbon tetrachloride, which is also a non-polar solvent. And as I told you guys, you don't need to know which compound is a polar or non-polar or solvent. What I tell you is that I will tell you this compound or this solvent is polar or non-polar, and then you have to be able to tell me if it's soluble or not. Then basically, polar compounds in polar solvent, non-polar compounds in non-polar solvents, and compound containing hydrogen bonding are soluble in water. Okay, that's all I need to know. I don't want you to be able to recognize the compounds or the solvents to be polar or non-polar. Just know this fact. Now let's talk about solubility. Talk about those substances that are insoluble in water. Okay, then going back to 3 slides before, then ionic and polar compound, you could dissolve them in polar solvent, which water is one of them. Now what about non-polar compounds? Okay, non-polar compounds, and a lot of hydrocarbons are non-polar, like oil. Oil is a hydrocarbon, it's non-polar. Then what do we do if we want to dissolve it in water? Okay, to dissolve non-polar compounds in water, you're going to use additive, and that additive called surfactant. Okay, that surfactant has a polar end or polar tail and a non-polar tail. Okay, then what happens to that? The non-polar compound, okay, will be dissolved in the non-polar tail of the part of the surfactant, and the water dissolve, which is polar, it dissolves in the polar tail of the surfactant. Then whenever you want to dissolve a polar compound in a non-polar compound in a polar solvent, you have to use an additive. Okay, and that additive, which we call them surfactant, has a polar tail and non-polar tail. Then those compounds that are non-polar will be dissolved in the non-polar tail part of the surfactant, and those parts like water that are polar will be dissolved in polar tail of the surfactant, and that ends up with a homogeneous solution. Okay, then on their own you cannot dissolve non-polar compound in polar solvents. You have to use an additive, and these additives comes with a polar and non-polar tail. That way you will be able to dissolve them. Now what about the solubility of gases? Okay, then solubility of gases in water decreases with increasing temperature. Okay, then as you could see here, the solubility of gases, in another word, solubility of gases in water is indirectly proportional to temperature. Okay, that means if you increase the temperature, the solubility decreases, and if you decrease the temperature, solubility increases. Okay, then they are indirectly proportional. If you increase one, the other one decreases. Okay, one more time. If you increase, what it means is that if you increase the temperature, solubility, I'm going to write it as SOL, of gases decreases. And if you decrease this temperature, the solubility of gases increases. Okay, they are indirectly proportional. Okay, and that sign is a proportionality sign. Okay, that tells you about proportionalities. Okay, all right, now let's talk about Henry's law. Okay, that talks about the solubility of gases in liquid. Okay, whereas solubility of gases in liquid is directly proportional to pressure. Okay, which is Henry's law. I talk about Henry's law when I teach that chapter that involves gases. Okay, but for now you will know that the solubility of gases in liquid is directly proportional to pressure. Okay, that means if you increase the pressure, the solubility increases of gases, and if you decrease the pressure, the solubility of gases decreases. Okay, it's Henry's law. Then let's go over this one more time. When we talk about the solubility of gases in water, it depends on two factors. Okay, one is temperature. Okay, then solubility of gases in water is indirectly proportional to temperature. That means if you increase the temperature, the solubility of gases decreases, and if you decrease the temperature, the solubility of gases increases. Then as you could see, they are indirectly proportional. Now let's talk about the solubility of gases in regard to pressure. Then the solubility of gases, they are directly proportional to pressure. That means if you increase the pressure, the solubility of gases increases, and if you decrease the pressure, the solubility of gases decreases. Okay, okay, now let's talk about the can of Coke that we all love to drink, which applies to this fact that I just told you guys. Okay, now what you have a can or like a bottle of Coke. Okay, one is cold, one is warm. Then if you open the cold can of Coke, okay, what it is, it doesn't fuzz out, the gases doesn't fizz out as much. Whereas for the warm soda, it will bubble out a lot. Okay, that's exactly what it is when they talk about the solubility of gases in regards to temperature. Okay, then if it's cold, okay, that means the temperature is low. Okay, that's why more of the gases are dissolved, the solubility increases. Then most of the gas is in the Coke. Okay, but whereas when it's warm, at warmer temperature, which is higher temperature, the solubility of gases decreases. That means that you will get That means less of carbon dioxide is dissolved in your Coke. That's why you will see more fuzzing. Okay, then that is something that you will see in everyday life. Okay, which you could do it on your home. Just put a can of Coke in the fridge, leave it outside and open it. You see that the warmer one fizzes a lot more because the gases are less soluble, whereas in the colder one the gases are more soluble. Alright, now let's talk about the solubility of gases in terms of pressure. Then, as I told you guys, the solubility of gases is directly proportional to pressure. That means if it's higher in pressure, the solubility of gases is higher. And if it's lower in pressure, the solubility of gases is lower. Then, as you could see in this can of Coke, as soon as you open the can of Coke, do you see a lot of the carbon dioxide comes out? You will feel it kind of on your hand as soon as you open it. Okay, that means you are releasing the pressure. As soon as you open the can, you are releasing the pressure. When you are releasing the pressure in this particular example, the solubility decreases, whereas in a closed can the pressure is still high. That's why the solubility is high, whereas in this one, when you are opening the can, the pressure goes down. That's why the solubility is also going down. Okay. Now let's talk about mass percent composition. Mass percent composition is the concentration basically mass percent is the number of grams of solute dissolved in 100 milliliter of solution. Okay. Sometimes when we talk about the fact that a solution has a concentration of 14% by mass, that means 14 grams of solute is dissolved in 100 grams of solution. As you could see here, again is solution, okay, which is the sum of solute and solvent. Also, when we talk about a concentration of solution, basically we are talking about how much solute is dissolved in a specific amount of solution. If you add a lot of solute, okay, the concentration is higher, whereas if you add less solute, the concentration is lower. Okay, the mass percent is basically the grams of solute dissolved in 100 milliliter of solution. This is the equation to calculate mass percent composition, which is the grams of solute over grams of solution, okay, or grams of solution. And since it's in percentile, we have to multiply it by 100 to make it to percentile. Okay, this equation you don't need to memorize, it will be given to you if you need them. Now let's do this example. In this example, what we're going to do, we want to calculate the mass of carbon dioxide is dissolved. Okay, then what we know in here, we know the mass percent. Okay, then if I go back to my previous slide, then we do know the mass percent. What we want, this one we want to calculate. Okay, this is what we're going to calculate. All right. But one thing that we also have, we know the volume of water solution. Okay, the volume is 28.6 liter, and the density of that water solution is also given. Okay. Then knowing the density, knowing the volume, we could find the mass of the solution. then if I go back to my previous slide, then I will have the grams of solution and I will have the mass percent, and I could easily calculate the mass of the solute. Okay, all right. The density, which is 1.03, is equal to mass over volume. Then as you could see here, the volume is in liter. We have to convert it to milliliter times 10 to the power of 3 milliliter. Okay, and if you do the math, okay, we cross multiply. Okay, that means you multiply 1.03 by 28.6 times 10 to the power of 3. Then the mass of your solution will be equal to, okay, 294.58 gram. Now we have to take care of the sig fig part of it. This number is 3 sig fig. That number is 3 sig fig. Your answer has to be 3 sig fig, which will be equal to 2.95 times 10 to the power of 4 grams. This is the mass of your solution. Now, then you have the mass percent. Since the mass percent is multiplied by 100, then to put that number, I divide it by 100, or just leave it like that, okay? 8.5 is equal to mass of carbon dioxide over the mass of solution, which we calculated it, 2.95 times 10 to the power of 4 grams times 100. Okay, then if you do the calculation, the mass of carbon dioxide will be equal to 2507.5 grams. Once you know the mass of carbon dioxide, now we have to take care of the sig fig. This number is 2 sig fig, and this number is 3 sig fig, when 100 is just a number with unlimited number of sig fig. Between 2 and 3, I'll choose 2, that has the least sig fig. And when we round up this number, you will get 2.5 times 10 to the power of 3 grams. Okay, then this will be the mass of carbon dioxide in grams dissolved in that water solution. Okay, now let's talk about molarity. Molarity is a very important concept in chemistry. It's basically the same as concentration. That's another name for concentration. When we talk about molarity, it's the moles of solute dissolved per liter of the solution. That's the definition of molarity. The molarity is the same as concentration. Okay, sometimes we talk about the concentration of solution or the molarity of the solution. It's just exactly the same thing, and by definition is the moles of solute over the liter of solution. Again, it's solution. One thing that a lot of students make a mistake is that they forget to convert the volume from a milliliter or any unit to liter. You have to make sure that the unit or the volume is in liter. Why? Because the unit for molarity or concentration is mole per liter. Okay, which we also write it as capital M. Okay, you can write it either or. Okay, this conversion or this equation, you have to know it. It will not be given to you. Now let's do this problem. Okay, let's do it this way. What we want to do here, you want to calculate the volume of the solution. Okay, then the concentration, it's 0.05 0.30 m, which is mole per liter. That's the concentration. Okay, and the mole is 0.025. Now you want to calculate volume. Okay, then that's what we're gonna do. Okay, then what we're gonna do here, you're gonna set up this equation. You could use the molarity equation. You could plug in the numbers and calculate it, or you could use it in a way, you could set it up so that you will cancel out moles and you will end up with volume. Okay, then if you set it up as 0.025 mole, okay, times, then in order to cancel out moles, okay, then the mole has to be down here and the volume has to be up there. Okay, and if you do the math, what you have to do here, you have to divide 0.025 by 0.3. Okay, as you could see here, the moles, that's not a good color, the moles gonna cancel out and what you will end up with is liter. Okay, we are now multiplying 0.025 by 0.30. We are dividing. Okay, then 0.025 divided by 0.30 will be 0.08333 liter. Now next we have to take care of the sig fig. To sig fig, to sig fig, the answer is 2 sig fig. 0.083 liter. Okay, that is the volume in liters. Since the question asks us in liter, we leave it in liter. Okay, then what I did was that you could use this equation, or you could use it in terms of in a one-line dimensional analysis, as we've talked in the past. Then you're gonna set it up so that you could cancel out the moles and you end up with volume, and that's how we do it. Let's do the second one. Okay, for the second one, you want to calculate the molarity. Okay, you know the mass of sodium hydroxide and you know the volume of the solution. To calculate molarity, we divide moles of sodium hydroxide by the liter of solution. We don't have the mole. What we have here, we have the mass. Then what we have to do is to convert the mass to mole. Okay, mass of sodium hydroxide to the moles of sodium hydroxide, and then to molarity or concentration of sodium hydroxide. If you put sodium hydroxide in a bracket like this, that means we are talking about concentration of sodium hydroxide. Okay, then here is 20 gram. We use the molecular weight of sodium hydroxide, okay, which is 39.99707 grams. Okay, here you find mole, and then the concentration is mole per liter, which is divided by liter. And as you could see here, if I do it, the gram's gonna go and I will end up with mole per liter. Okay, which is gonna be exactly 2. Then if you do that in your calculator, you will get number 2. Okay, that's what you will get, number 2. But if you think about the sig fig, this number is 3 sig fig, that number is 3, 4, 5, 6, 7 sig fig, and this number is 2 sig fig. That's why you have to put 0.0 to make it a 2 sig fig. Okay, If you leave it at 2, that 2 will be 1 sigvig, which will be wrong. You have to add a 0.0 to make it 2 sigvig. Now let's talk about the concentration of ions. Okay, concentration is molar. Okay, that means it consists of mole. Remember when we were converting between the number of moles using the chemical formula? That's exactly the same thing. Okay, for example, if you are considering calcium chloride, okay, then calcium chloride is 1 mole is proportional to 1 mole of calcium ion and 2 mole of chloride ion, right? Let's write the state of it too. Okay, that's why we could easily convert the concentration, the molar concentration of calcium chloride to the concentration of calcium ion and chloride ion. Okay, then as you could see, for the first one, to convert the molar concentration of calcium chloride to calcium ion, as you could see here, it's a 1-to-1 ratio. Okay, it's a 1-to-1. I could rewrite it like this. Okay, 0.25 m of calcium chloride. Okay, then it's 1 mole of calcium ion proportional to 1 mole of calcium chloride. And as you could see, it's 1-to-1. Okay. It's exactly the same thing. Now, we're going to convert the molar concentration of calcium chloride to chloride ion. And based on this chemical formula, 2 moles of chloride ion is proportional to 1 mole of calcium chloride, which is twice as much. Okay, this is equal to 0.50 molar chloride ion. Okay, that's basically, it's the same thing. We're going to use the chemical formula to convert the molar concentrations from one species to another one. Now let's do this problem. You want to calculate the molar concentration of sodium ion and phosphate ion in 1.50 molar sodium phosphate. Then 1 mole of sodium phosphate, as you could see here, is proportional to 3 moles of sodium ion and 1 mole of phosphate ion. Okay, this is 3-to-1 ratio. Now I have 1.5 mole of sodium phosphate. I'm going to set up my equation so that the moles of sodium phosphate gonna go and I end up with moles of sodium ion, okay, which is 3 times as much. Then as you could see here, the moles of sodium phosphate gonna go and I end up with sodium ion, which is gonna be equal to 4.50 of sodium ion. Okay, now we're going to do the same thing to find the molar concentration of phosphate ion. Again, 1.50 molar sodium phosphate. I'm going to set up my equation so that the moles of sodium phosphate are going to go and I end up with phosphate ion. Okay, then as you could see again here, the sodium phosphate gonna go, and since they are 1-to-1 ratio, I have the same molar concentration for phosphate ion. As you could see in this example, I was able to use the chemical formula and the molar constant and the molar values to convert the molar concentration of sodium phosphate to molar concentration of sodium ion and phosphate ion. Now, how do we make a standard solution? By definition, a standard solution is a solution of known concentration. Okay, then if we know the concentration of your solution, we can make it from the scratch. Why? Because when we are making solutions, okay, once you know the concentration, remember, concentration is equal to mole over volume. Then when we want to make a standard solution, we know the concentration, we know the volume. Okay, then if you look at this particular example, you know the volume. Okay, you know the fact that you told the volume is 1 liter. Okay, and you know the concentration is 1 molar. Okay, then we know the concentration, we know the volume. Okay, then what you want to do, first you want to find the number of moles. Okay, right, then you know the concentration, you told it this much, and you know the volume, you know that the volume is in 1 liter. Okay, the volume is in 1 liter, you will be told, because there is no way you could do the calculation if you don't know the volume. Then you're going to set up the equation so that you will end up with the number of moles. Okay, then if you set it up like this, as you could see here, the volume cancel out and you will end up with the number of moles, which is 1 mole. Okay, now once you know the mole, you need to convert it to mass. Okay, you know the molar mass of sodium chloride, which is 58.44 gram per mole. Then I'm going to convert the mole to mass. Okay, then 1 mole of sodium chloride for this example is 58.44 gram. That's the molecular weight of sodium chloride. Okay, then here I set it up my equation so that the number of moles is going to get canceled out and I will end up with mass, which is equal to 58.44 gram. Okay, now this number is 3 sig fig. This number is 4 sig fig. Your answer will be 3 sig fig, which is equal to 58.4 gram. Okay, then what you will do, you will go to a scale, okay, to any scale, and you weigh out, measure 58.4 gram, or as close as possible to 58.4 grams of sodium chloride, solid sodium chloride. Okay, I'll put it as in dot since it's solid. And what you want to do, since you know the volume of your solution that you're making is 1 liter, these are called these are called volumetric flask. Okay, let me write it volumetric flask. Then what you will do, you will gonna go and get a volumetric flask that's 1 liter. Okay, and these are calibrated for. Okay, then once you weigh that at as close as possible to 58.4 grams of sodium chloride, you transfer that solid sodium chloride into your 1 liter volumetric flask. Okay, and once you've done, you're gonna fill the rest with water. When you look at the volumetric flask, if you look at the neck of the flask, as you could see here, there is a line. There is a white line on the neck of the flask. That's the calibration. That means you're gonna fill the water so that the bottom of the meniscus inside at the bottom of the meniscus of the water is in line with the line on the neck of the flask. Okay, that's what you want to see. Okay, then you will add as much water so that the bottom of the meniscus of the solution inside the volumetric flask is in line with the line on the neck of the flask. Okay, if you overshoot it, that means your solution concentration is not 1 molar anymore. You have to throw everything out and start from scratch, which is measuring the mass of your salt and do all of that. Okay, that's why what we do when we are adding DI water, what I forgot to say, you have to make sure that's DI water. When we add DI water, you want to get it as close as possible to the line, and then for the next couple of drops, you're going to add a drop of water at a time to make sure you do not overpass that bottom of the meniscus. Then once the line of the solution is in line with the line on the neck of the flask, you're going to put the cap on. These volumetric flasks come with a cap, and you're going to invert it 25 times so that you mix it and you get a homogeneous solution. Okay, then here you will end up with a solution with a concentration of 1 molar, and it is 1 liter. Okay, then that's how we make standard solution. Just go over it one more time. When we are making standard solution, by definition is a solution of known concentration. You're told the molarity of your solution is 1 molar, and you were told the volume is in 1 liter. Okay, then the first thing that you want to do is to convert the concentration to number of moles to mass. Okay, and from that you will know the mass of sodium chloride that you have to weigh out. Then once you know you have to measure 58.4 grams of solid sodium chloride, you go to the scale and you measure as close as possible to that number. Once you get that number, you transfer your solid sodium chloride to your 1 liter volumetric flask. And as I told you guys, these flasks are calibrated for. Okay, then if you need your solution to be 1 liter, you have to go and get 1 liter volumetric flask. These flasks come in so many different volumes. They come in even like 1 milliliter. Okay, so many different sizes, depends on what size you need. Once you transfer all the salt into your volumetric flask, you're gonna fill the flask to the line with DI, distilled or deionized water. You want to make sure that you do not overpass that white line on the neck of the flask. In order to do that, you're going to add water as close as possible to the line, and for the next couple of drops, add 1 drop at a time. Once the bottom of the meniscus inside the solution is in line with that line on the neck of the flask, you're going to stop adding water. You're going to put the cap back on, and you're going to invert your flask about 20 to 25 times so that the solution gets completely mixed up. And at the end, what you have a sodium chloride solution with a concentration of 1 molarity in a 1 liter volumetric flask. That's how we make standard solutions. Now let's talk about dilution. Dilution, by definition, is where we go from concentrated solution to a less concentrated solution. It's just the same concept of your strong coffee in the morning. Then when your coffee is too strong, you add some more hot water. That's why you are diluting it down. Then basically what it is, when we are doing dilution, what we do is that we go from higher concentration solution to a lower concentration solution. Okay. Then as you could see in this picture, the number of moles remains the same. Okay. The only thing that's different is that the volume of the solution changes. Okay. That's the only difference. But you have to make sure in dilution the number of moles stays the same. Only the volume changes and the concentration changes. These are the two things that change during dilution. Then volume changes. We have volume and concentration. They change. Whereas number of moles remains the same. Okay, and that's really important to know. And here, if you look at this beaker, this is a concentrated solution. Look at this beaker. It's a concentrated solution. And when we add more solvent, it becomes diluted solution. Okay. Now, since the number of moles stays the same, okay, if you think about concentration equation that we talked about, then concentration, which I'm going to call it M, okay, is equal to moles over volume, right? Okay. Then if we are talking about diluted solution and concentrated solution, if concentrated solution we call it 1, okay, then M1, or what I could say mole mole 1 is equal to M1 times V1. That's for concentrated solution. Okay. The initial solution. Okay. This is what I'm talking about, the concentrated solution. I call it 1. And diluted solution, I call it 2. Okay. Then for diluted solution, then if diluted solution, I give it number 2, then the moles of diluted solution is equal to M1, which is the concentration of diluted solution, M2 times V2, which is the volume of diluted solution. Now here, as I told you guys, during dilution the number of moles stays the same. That means mole 1 is equal to mole 2. Okay, then if mole 1 and mole 2, if mole 1 is equal to mole 2, which is basically the number of moles in a concentrated solution and the number of moles in diluted solution, they are the same. What we result is that M1 V1 is equal to M2 V2. Okay, this is the dilution equation which you need to know. One thing that you want to pay attention is that the unit for concentration on each side, it has to be the same. The volume on each side, it has to be the same. The volume could have any unit, the concentration could have any unit. As long as the two units are exactly the same, it's fine. The volume unit does not necessarily have to be liter. If you want to choose it to be liter, then the volume for V1 has to be liter, V2 has to be liter, okay? But as I told you guys, the units for M1 and M2 or V1 and V2 could be any unit as long as it is the same. Now let's do this problem. Then what you want to do, you want to calculate the concentration of a solution that is formed by diluting 5 milliliter of a 3.2 molarity glucose to 400 liter. Okay, then these are, okay, and this is your V1, this is your M1. These are concentrations and volume before dilution, and that's after dilution. Okay, and M1 V1 is equal to M2 V2. Then M1 is 3.2 V1. If you look at the units for, sorry, that one should be V2. If you look at the units for V1 is in milliliter, or V2 is in liter. Okay, as I told you guys, the unit has to be the same. You could either convert the unit for V2 from liter to milliliter, or convert the unit for V1 from milliliter to liter. It's your choice. Whichever you want to do, it should be the same. Okay, I choose to convert the unit for V1 from milliliter to liter. That's just the optional choice. Okay, which is equal to M2, which we want to find out, times V2, which is 400. Okay, then as you could see here, the unit for my V1 is liter, V2 is liter. Okay, as I told you guys, it could be any unit as long as it's the same, it's fine. Now if you do the math, our M2 will be 4 times 10 to the power of negative 5 molar. Okay, now we have to take care of the sig fig. This number is 2 sig fig. This is 2 sig fig, and 400 is 1 sig fig. That's why our answer has to be 1 sig fig, as it is. Okay, then our the concentration for a concentrated solution is 4 times 10 to the power of negative 5 molar. Okay, then as you could see, if you compare your M1 and M2, you will see that M2 is a lot less concentrated because it's a lot more diluted. Okay, let's do another problem. What you want to find out here, it says, what is the volume that you use when you dilute 0.100 liter of a 15 molarity sodium hydroxide solution to get 1.0 molarity sodium hydroxide solution? And this is your diluted solution. I'm going to call it M2. This is your concentrated solution, and that's the concentrated concentration. Okay, then when we plug in the numbers using the dilution equation, M1, sorry, I made a mistake here, that one should be M1. M1 is 15 V1 is 0.1 M2 is 1, and V2 we want to find out. And also make sure that the unit for concentration is the same on each side, and it is the same on each side. Then if you do the little math, V2 is equal to exactly 1.5 liter. Okay. Now for sig fig, this number 15 is 2 sig fig, 0.100 is 3, and 1.0 is 2. That's why your answer has to be 2 sig fig, which is 2 sig fig. You don't need to do the dotted. Since you have your number as exactly 2 sig fig, you don't need to do the dotted line and all of that. Okay. Now, let's talk about how to make diluted solution. Okay. Then in the previous slide, when we talk about making standard solution, okay, you guys learned how to make a standard solution. Now, how do we make a diluted solution? All right. What we want to do here, we want to make a 500 milliliter 2.00 molarity sodium chloride solution from 5 molarity sodium chloride. Okay, and this one is our V2, this one is your M2. Then these are your diluted or your final concentration and volumes, and this is your initial, which is M1. Then what you want to calculate, how much of the concentrated solution, the 5 molarity, that you want to pipe it out. This is called pipette. Okay. Okay. I think I'm not sure if it's 1p or 2p pipette. Okay, I put it 1p. Okay. Then you need to know how much of a concentrated solution you need to pipe it out in order to make a diluted solution that's 2 molarity and it's in 500 milliliter. Since every single digit in these type of measurements or experimentation matters, you have to use volumetric Lasper. Then you have to use, since you want the concentration of your final solution to be 500 milliliter, you have to be using a 500 milliliter volumetric flask. Okay. Then what I'm going to do here, I'm going to measure to see how much of a concentrated solution I have to pipe it out. Okay. Then M1. Okay, then use the dilution equation, which is M1 V1 is equal to M2 V2. Then M1 is 5. V1 we don't know. M2 is 2. And V2 is 500. Okay, now let's do the calculation. Then V1 is equal to 2 times 500 divided by 5, which is 200 milliliter. Okay, let's give it for now 200 milliliter. Now I have to take care of the sig fig. This number is 3 sig fig, 5.00. 2.00 is also 3. And 500 point is also 3. Then 333, then my answer has to be 3. Then if you look here, 200 right now is 1 sig fig. But as soon as I put a decimal sign here, I make it out to be 3 sig fig as well. Then what we have to do, we have to pipette 200 milliliter of concentrated solution, okay, and transfer it into a 500 milliliter flask, and then add DI water as much as the volume of the solution in the flask, the bottom of the meniscus is in line with the line on the neck of the flask, as you see in this picture. Okay, then when the bottom of the meniscus, okay, of the solution inside the flask is in line, I didn't do a really good job. Okay, and it's in line with the line on the neck of the flask. Then don't stop adding any DI water. You're gonna cap it. I'm gonna invert the solution between 20 to 25 times in order to get your a homogeneous mixture. And once you achieve that, what you want to do is you're gonna you're gonna store it or gonna use it. Okay. Then when you want to make a diluted solution, the first thing that you want to do is to make sure how much of a concentrated solution you have to pipe it out. Then once you do the calculation, as I did here, you will know that you need 200 milliliter of the concentrated, which is 5 molarity solution. Then once you pipe it out 200 milliliter, okay, you're going to transfer that into our 500 milliliter volumetric flask. Why 500 milliliter volumetric flask? Because your final volume, or the volume of your diluted solution, it says 500 milliliter. That's why we need to use 500 milliliter volumetric flask. Then you're going to transfer 200 milliliter of your concentrated solution into the flask. You're going to fill the flask with water up to the line. Once the bottom of the meniscus of the solution in the flask is in line with the line on the neck of the flask, you're going to place the cap. Okay, that's the cap. And you're going to invert it between 20 to 25 times. And what you will have here, you will have a diluted solution which has a concentration of 2 molarity. Okay, that's the concentration of your 500 milliliter solution. Okay, this one is 2 molarity and it's in 500 milliliter. Alright, now what we're going to do next, we're going to talk about stoichiometry when we are dealing with concentrations. Then we've already talked about stoichiometry, that when it was, we talked about molarities, we talked about number of moles and masses, and what you had to do is to find the limiting reactant, and from the limiting reactant you will convert the moles of the limiting reactant to the mass of the product. Okay, now here, instead of the number of moles or even the masses, we have concentration. Okay, and that's the only difference. Everything else is stayed the same. Then what you have to do here, once you wrote your balanced chemical equation, okay, that's step 1. Once you write your balanced chemical equation, you want to convert the concentrations to the number of moles. Okay, and then you want to find out which one of them is limiting. Okay, and then once you find the limiting, then you will find that, and you use that to find the mass or the concentration of the product. Okay, oopsie, stop. Now what we're going to do this problem. Okay, now let's do this. It says 10 milliliter of a 0.3 molarity sodium phosphate. Let's write sodium phosphate reacts with, okay, then the volume is 10 milliliter, the concentration is 0.3 3 molarity. Reacts with 20.0 milliliter of a 0.2 molarity lead to nitrate. Okay, then the volume is 20. And the concentration is 0.2. Now A asks you what precipitate will it form. And what we have to do is to write a balanced chemical equation. Okay. Then we will produce sodium nitrate, which is an aqueous product, plus lead 2 phosphate. Okay. Then if you look at your solubility handout, this product, lead 2 phosphate, is a salt. Then this is your precipitate. Okay, that's the precipitate that we form. That's our precipitate. Okay, now for part B, you want to know what mass of precipitate will form. Okay, that's what we're gonna do. What you're gonna do is to find the mass of, if I go back, you want to find the mass of lead 2 phosphate that we're gonna produce. Then, as I told you guys, what you want to do here, we consider sodium. Let's do sodium phosphate first. Then you're gonna convert the concentration and the volume of sodium phosphate to the moles of sodium phosphate, and then the moles of sodium phosphate to the moles of your precipitant, and then the moles of precipitant to the mass of precipitant. Okay. Also, you're going to do the same thing with lead 2 nitrate. You're going to use the volume and concentration to find, and use those numbers. You'll find the moles of lead 2 nitrate. Then you're going to convert the moles of lead 2 nitrate to the moles of lead 2 phosphate, and then to the mass. Then the reactant that produces the least amount of product or the precipitant is your limiting, and that mass will be the mass of your precipitant. But one other thing that we have to do before we move on is to balance this reaction. Okay, that's important to do. We have 3 sodium on the reactant side, okay, and we have 1 on the product side. Now, if you look at lead, we have 3 lead on the product side, and we have 1. That's why I'm going to add the coefficient 3 in front of lead 2 nitrate. And also we have 2 phosphate ion on the product side. That's why I add a coefficient 2 in front of sodium phosphate on the reactant side. Now the number of leads and phosphate ion on each side is the same. Now as you could see here, we have 6 nitrate ion and 6 sodium ion. I'm going to add a coefficient 6 here. As you can see here, now this equation is completely balanced. Now we could go and do the calculation. Okay. Then what I'm going to do, I'm going to quickly write out a balanced chemical equation right up here. Sodium phosphate plus 3 lead 2 nitrate produces 6 sodium nitrate and lead 2 phosphate. Then step 1, I'm going to convert the moles. I'm going to use sodium phosphate. Okay. Then what I'm going to do, I'm going to convert the concentrations. Then we have 0.30 mole per liter times, as you could see, the volume is in milliliter. I have to convert it to liter. Okay, so then here, as you could see here, the liter is going to go, and I will end up with moles of sodium phosphate. Now that I have the moles of sodium phosphate, I'm going to convert the moles of sodium phosphate to the moles of the precipitant. Then based on this balanced chemical equation, let me write it, Na3PO4. Okay, I'm going to set it up so that the moles of sodium phosphate are going to go, and I end up with moles of the precipitant. Then it's 2 moles of sodium phosphate is proportional to 1 mole of lead 2 phosphate. And then now that I have, as you could see here, let me do that. Let's do that. I cancel out the moles of sodium phosphate. I end up with moles of the precipitant. Now I need to convert the moles of precipitant to its mass using the given molecular weight for the product or the precipitant. Okay, then based on the definition of molar mass, 1 mole of sodium phosphate is equal to 811.5427 gram. Okay, also here, as you guys see, the moles of lead 2 phosphate gotta go, and I will end up with mass of lead 2 phosphate, which is going to be equal to 1.217310405 grams of lead 2 phosphate. Okay, the next thing that you have to do is to find the sig fig. This number is 2.30 is 2 sig fig, 10.0 is 3 sig fig, 1 and 2 are just numbers, and 811.5427 is 3, 4, 5, 6, 7 sig fig. Therefore, between 2, 3, and 7, we choose 2. Okay, and that will be equal to 1.2 grams of lead 2 phosphate. Okay. All right. Now, we're going to do the exact same thing with lead 2 nitrate, because we're going to see which one of the two is the limiting. Okay. Now let's choose a different color. I'm going to choose dark blue, and I'm going to do the exact same type of thing with lead 2 nitrate. Okay. Now what we're going to do, we're going to convert the concentration of lead 2 nitrate don't know why it's doing that. Okay, moles of Okay. So I'm going to convert the concentration of lead to nitrate to small. It has to be 20.0 times 10 to the power of -3 liter. And as you could see here, I set it up the equation so that the volume is going to go and I end up with mole. Also keep in mind that about 20.0 is a milliliter. You have to convert it to liter as I did here. Now, as you could see here, the volume's going to cancel out. Okay. Now the next step, I want to convert the moles of lead to nitrate to the moles of lead to phosphate, which is our precipitant. And based on the balanced chemical equation, 3 moles of lead to nitrate is proportional to 1 moles of lead to phosphate. Okay. Also, as you can see here, the moles of lead to nitrate gonna go. And last, we want to find the mass of lead to phosphate, which we're gonna use the molar mass of lead to phosphate and convert its mole to its mass. Okay, 1 mole of (811.5427). Okay, and also as you could see here, I could easily cancel the moles of lead to phosphate. Then if you do the calculation, the mass of lead to phosphate will be 1.0820569 grams of lead to phosphate. Okay, and we have to take care of the sig fig. This number is 2 sig fig. This number is 3 sig fig. And 811.5427 is 7 sig fig. Then 237, we go by 2. Okay, therefore the mass of lead to phosphate here is going to be 1.1 gram. Now what we're going to look here is to find the limiting reactant. Then for sodium phosphate produces 1.2 grams of lead to phosphate, and lead to nitrate, which is the second reactant, produces 1.1 grams of lead to phosphate. Then between these two masses, this one is the smaller of the two, okay, which makes lead to nitrate a limiting reactant, and it makes this value our theoretical yield or the mass of precipitant. Okay, then let's write it. Since lead to nitrate produces less amount of precipitant, therefore lead to nitrate is the limiting reactant, and therefore mass of the precipitant is equal to, which in our case the precipitant is lead 2 phosphate is 1.1 gram. Okay. Now, this is the mass of precipitant. That's the question that we were asked to calculate. We were asked to calculate the mass of precipitant from the given numbers, which were the concentration and the volume of each of the reactant. Now, for part C, we want to calculate what is the concentration of phosphate ion left in the solution after the reaction is completed. It's kind of the backward calculation. Then, since lead 2 nitrate is the limiting, we use all the lead 2 nitrate. Okay, we will have no lead 2 nitrate, but we will have some sodium phosphate left over, because sodium phosphate is the excess. Okay. When the question asks, what is the concentration of phosphate ion left over? Then what we have to do is to convert the mass of, which is 1.1 grams, of lead 2 phosphate to the moles of sodium phosphate, which is the excess. Okay, then let's do that. We want to convert the mass of lead 2 phosphate to the moles of sodium phosphate, since sodium phosphate is our excess. Okay, then we calculated in part B that we have 1.1 grams of lead 2 phosphate. Okay. Then we're going to convert the mass of lead 2 phosphate to its mole. Okay. Using the molecular weight of lead 2 phosphate. And then the moles of lead 2 phosphate to the moles of sodium phosphate. Then based on the balanced chemical equation, the moles of sodium phosphate to lead 2 phosphate is 2 to 1. Okay, it's 2 to 1. And 2 moles of sodium phosphate is proportional to 1 mole of lead 2 nitrate. Sorry, lead 2 phosphate. Okay. Now, just to double check, here the masses of lead 2 phosphate gonna go, and here the moles of lead 2 phosphate gonna go, and I will end up with moles of sodium phosphate, which will be equal to 2.710886 times 10 to the power of negative 3 moles of sodium phosphate. Just like any other time, we have to take care of the sig-fig. 1.1 is 2 sig-fig. The molecular weight is 3, 4, 5, 6, 7 sig-fig. Then between 2 and 7, we choose 2. Okay, and this will be the number of moles of sodium phosphate being used. Okay, this much is used. Okay. Then what we're gonna do next, okay, if I go back or even look here, we use this many number of moles. How much did we start with? Because we have to find out the moles of leftover, okay? Then here, to know how much we started with, okay, it's 0.3 mole per liter times 10.0 times 10 to the power of negative 3 liter. This will be 0.030. This is the moles of sodium phosphate we started with. Then we started with 0.0030 moles of sodium phosphate. We used 2.7 times 10 to the power of negative 3. Now what's the leftover? It's going to be just a subtract. It's like you have 5 tomatoes, you eat 2 of it. How many left over? 5 minus 2, which is 3. Exactly the same thing. And it's 0.0030 mole minus 0.0027. 2.7 times 10 to the power of negative 3 is the same as 0.0027. Okay? 7 mole. Then when you subtract these two numbers, you get 0.0003 moles of sodium phosphate left over. Now the question doesn't ask us about the moles of sodium phosphate, it asks us about the concentration of phosphate ion. Then based on this chemical formula, 1 mole of sodium phosphate is proportional to 3 moles of sodium ion and 1 mole of phosphate ion. Okay, and these are the two that we are caring about, which is a 1-to-1 ratio. Then what you have to do here, you want to convert the moles of sodium phosphate to the moles of phosphate ion, which is a 1-to-1. Which we will get the exact same. Oops. Okay. As you can see here, the moles of sodium phosphate gonna go, and you will end up with this many moles of this many moles of phosphate ion. Once you know the moles of phosphate ion, you could easily calculate the concentration of phosphate ion. Okay. Then the concentration of phosphate ion, let me choose a different color. I want it to be too many. Okay. Now the concentration of phosphate ion will be the moles, which is 0.0003 mole over the volume. Here the volume should be the combined volume. Should be 10 milliliter plus 20 milliliter. Okay, then it's 10 plus 20. Okay, and we have to times 10 to the power of negative 3 to convert it to liter. Okay, which is equal to exactly 0.01 molar phosphate ion. Okay, this is the answer. This is the concentration of phosphate ion left in the solution. Okay. Then just going back, talk about it one more time. Then this part asks you to convert or to find out the concentration of phosphate ion left over. Then in order to do that, you have to calculate, or you have to convert the mass of lead to phosphate that you calculated it in part B and convert it to moles of sodium phosphate. That will be the amount or the moles of sodium phosphate that you used. Knowing how much you started with and how much you used, when you subtract these two numbers, you will get the leftover moles of sodium phosphate. Now the question asks us for the concentration. That means you have to convert the moles of sodium phosphate to the moles of phosphate ion, which is a 1-to-1 ratio. And then you're going to divide that number by the total volume, which is 30. That means 10 is coming from here, 20 is coming from here, and you have to convert it to liter. Okay. Then when you do the division, the concentration of leftover phosphate ion is 0.01 molarity. Okay, and it's a right sig fig because this number is only 1 sig fig and that number is 3 sig fig. Between 1 and 3, the answer is 1. Now let's not talk about other concentrations unit. Okay, then since the last for the last couple of slides, we talked about molarity. Okay, that's one of the concentration. Now the other two are molality and normality. Okay, these are other concentration unit: molality and normality. Now, what is molality? Molality is the number of moles of solute per kilograms of solvent, not the solution. Okay, that's how molality is calculated. It's number of moles of solute per kilogram of solvent. Okay, it's kilogram of solvent, not the solution. Okay, now unlike mass percent composition that we use over the solution, here for molality we use solvent. Now let's do a little example. Then in this example, we want to calculate the molality of a solution containing 17.2 grams of ethylene glycol dissolved in 0.500 kilograms of water. Then if I go, then based on the definition of molality, you want to find the number of moles of solute per kilogram of solvent. Okay, then here the mass of solute is given. I want to find the moles of solute. Okay, then I'm going to convert 17.2 grams of ethylene glycol to the moles of ethylene glycol using the molar mass of ethylene glycol. Okay, which will be equal to 0.277106, 0.277106 moles of ethylene glycol. Okay, now let's do the sig fig. This number is 3 sig fig. Molar mass is 4 sig fig. Between 3 and 4, I choose 3. Here is the moles of ethylene glycol. 0.277 moles of ethylene glycol. Now that we have the moles of ethylene glycol here, I have the moles of solute and I have the kilogram of solvent. I could easily calculate molality. Okay, and molality is the moles of solute, which is 0.277 mole over kilogram of solvent, which is 0.500 kilogram of water. And when you do the math, it will be 0.554 exactly. And the unit for molality is lowercase m. Okay, that's how molality is calculated. Okay, it's the moles of solute, here is ethylene glycol, over kilogram of solvent, which is water, and it's 0.500. And for the sig fig, 0.277 is 3 sig fig. 0.500 is 3 sig fig, and as you can see, our answer is 3 sig fig. We don't have to do anything about it. It's already taken care of. And the unit for molality is lowercase m. Okay. Now, what's normality? The unit for normality is capital N. As you can see here, let me change it. Capital N. And normality concentrates on how many moles of hydronium ion or hydroxide ion we've got. Then to calculate normality, we multiply molarity by the number of either hydronium ion or hydroxide ion that we have. Okay. If you, for example, consider sulfuric acid, then as you can see here, how many units of hydronium does it have? It has 2 hydronium ion, doesn't it? That 2. Okay. Or like let's talk about magnesium hydroxide. How many units of hydroxide ion does it have? It has 2 units of hydroxide ion. Okay. That's what it means by each unit of hydronium or hydroxide ion. Okay. Then basically look how many hydronium ion or hydroxide ion we've got, and you multiply those unit numbers by molarity. Okay. Let's do this problem. In this problem, we deal with a solution of phosphoric acid, which contains 50.0 grams of phosphoric acid per liter of solution. Okay. Then we're going to calculate the normality. Okay. Then here it's 50 gram per liter of solution. Okay. Then what we want to do is to find out first, in order to calculate normality, we have to find the molarity and multiply it by the unit of hydronium ion. Okay. Then 50.0 gram per liter, I'm going to convert it to molarity, okay, using the molar mass or the molecular weight of phosphoric acid. Okay. Then I'm going to set up my equation so that the mass is going to go, and I end up with moles of phosphoric acid. As you can see, the gram's gonna go, and I will end up with a mole per liter of phosphoric acid. And then we take care of sig fig, 3 sig fig, and this number is 3 sig fig. Therefore, our answer is gonna be 3 sig fig. The mole per liter is the same as molarity, it's the concentration. Okay, and if you look here, 1 mole of phosphoric acid is proportional to 3 moles of hydronium ion. You see that? That's 3. Therefore, normality is equal to molarity, which is 0.554. 0.510 times the units of hydronium ion. Here has to be hydronium ion because we deal with acid, times 3, which will be 1.53, and the unit for normality is capital N. Okay? And that's how we calculate normality of phosphoric acid. This is the end of solution chapter.